Welcome to the vapor pressures of solutions. So, liquid solutions have significantly different physical properties than the pure solvent does. So, for example, a small amount of antifreeze is enough to significantly lower the freezing point of water and raise the boiling point of water. Another example is that a small amount of salt is used to melt ice on roads and sidewalks in the wintertime. We don't have to have a huge amount of salt on our roads or on our sidewalks. A small amount is enough to melt the ice and snow. So let's examine an experiment in which a sealed container encloses two beakers. So we've got our sealed container here, we've got our glass bulb, we've got two beakers in there. One of them has pure water, and one has a concentrated aqueous sulfuric acid solution. So the beaker on the left has the pure water, the beaker on the right has the concentrated sulfuric acid solution. So over time, the volume of liquid in the beaker containing the pure water, the one on the left, decreases, while the volume of liquid in the beaker containing the solution increases. So over time, we go from a case that looks like this to a case that looks like this. We end up having no water in the beaker on the left, and we've got significantly more water in the beaker on the right. So, the vapor pressure of the pure water is higher than the vapor pressure of the solution is. And this means that because there's water vapor in the space above, this means that the water solution, the pure water solution, is constantly losing water molecules to the gas phase, because if its vapor pressure is higher, it will lose water molecules to the gas phase until the vapor pressure of water above it is, or until the partial pressure of the water molecules above it is equal to the vapor pressure at that temperature. But the vapor pressure of that aqueous solution is lower, which means that as the water molecules evaporate from the beaker on the left and begin to saturate the air above the beaker on the right, well, now there's a higher partial pressure of water than the vapor pressure of the water in that beaker on the right. And that means that water molecules over time are going to enter the beaker on the right, because some of the water molecules are leaving the beaker, some of the water molecules are entering the beaker, but more molecules are entering the beaker than are leaving the beaker, and that means water enters the beaker over time. And that tends to dilute our solution. Our volume gets bigger, so our sulfuric acid becomes more dilute, our water becomes more concentrated. And this will happen until the beaker on the left is totally empty, because we have a concentration there of our solute of 0. We can't ever get the concentration in our two beakers to be the same, because we don't have any sulfuric acid there, so all the water has to leave that beaker and enter the beaker on the right, or stay in the gas phase. So again, the water molecules are evaporating from the pure water beaker, and they condense in the beaker containing our solution. And again, this is occurring because the system can only obtain equilibrium vapor pressure when the partial vapor pressure of gaseous water in the container is equal to the vapor pressure of the solution, which is lower than the vapor pressure of the pure water, so the pure water beaker has to be empty. It will continue to evaporate and increase the vapor pressure in the space above until there's no water left in the beaker on the left. So this effect that we see is one example that the presence of a non-volatile solute lowers the vapor pressure of a solvent. And this is occurring because an increase in the solute concentration necessitates a decrease in the solvent concentration. And that is the number of solvent molecules per volume has to decrease as we increase the number of solute molecules per volume. And that means that the partial pressure has to drop. As the concentration of our solvent is dropping, the partial pressure of our solvent has to drop as well. So the partial pressure of, or the vapor pressure of our solvent above the solution has to be lower than the vapor pressure of our solvent above the pure solvent. So this decrease in our solvent concentration decreases the rate at which solvent molecules leave the liquid phase and enter the gas phase, and this means that the vapor pressure has to drop. And this is Raoult's law. So Raoult's law says that the vapor pressure of a solution is directly proportional to the mole fraction of the solvent in solution. So that's symbolized by P solution is equal to chi solvent times P solvent naught. So P solution is the vapor pressure of the solution. So this is the vapor pressure of the solvent above that solution. The chi solvent is the mole fraction of the solvent in that solution. And P solvent naught is the vapor pressure of the pure solvent at that temperature. So this is the vapor pressure of the solvent, what would be the vapor pressure of the solvent at that same temperature if the solvent was pure. So before you've mixed in the solute. So you can see that the mole fraction is always between 0 and 1. That means that this value has to always be somewhere between 0 and this value. It can't ever be higher. It must be lower if there's any solute around at all. So this means that the vapor pressure of the solution increases linearly from a mole fraction of 0, so pure solute, to a mole fraction of 1, so pure solvent. And it increases linearly between there. That's what Raoult's law says. So that was the vapor pressure of solutions.